Alright, so in this video, I'm gonna be explaining another important article, but this time we have source free. It means that we don't have source, for example, for privacy issue. And there is an interesting research area which is called differential privacy. And so sometimes companies when they want to share they share their models. They don't share their data. So we don't have access to their data, but we have input-output access to the model. So for this reason, we can still remove the problem of domain shift. And so this paper in 2023 is very interesting. Existing domain adaptation literature comprises multiple techniques that align the label source and unlabeled target domains at different stages and predict the target labels. In a source-free domain adaptation setting, the source data is not available for alignment. We present a source-free generative paradigm that captures the relation between source categories and enforces them onto the unlabeled target data, thereby circumventing the need for source data without introducing any new hyperparameters. The adaptation is performed through the adversarial alignment of the posterior probabilities of the source and target categories. The proposed approach demonstrates competitive performance against other source-free domain adaptation techniques that can also be used for source-present settings. So D sub S is source dataset when N sub S represents the number of labeled training samples, Y sub S is the one-hot representation. And the dataset D sub S and D sub T are just drawn from distributions, but they share the same label space with identical K categories. So they have a generative model. We propose a generative paradigm to estimate the labels for a target dataset. Let the images from the target dataset be sampled from X. Then the corresponding labels are one-hot binary vectors of type Y, and K is the number of categories. The images and labels are sampled from an unknown target distribution. So we propose to approximate P of phi using a parametric model Q. So we approximate it by this Q, which is parametrized by the theta parameter. And in order to estimate theta, we begin with estimating the reverse Kullback-Leibler divergence. So this is the upper bound for this Kullback-Leibler divergence. It is upper bounded here, and in deriving equation 1 we have used just this law and the fact that expectation of log of P is less than 0. The right hand side of the equation 1 is an upper bound for KL divergence between the distribution of Q, which is our approximation, and the real P of T. Because we have unknown, this P of T is an unknown prior distribution. But we have this generative model Q of T such that we can approximate Q. We assume that P sub S and P sub T source and target are almost the same, which is reasonable along the lines of assumption of covariate shift. We model Q, that our approximation, using a neural network which take X input and yields the posterior as output. The proposed model has issues of identifiability. A model is identifiable when P of X has a unique decomposition. If a swapping of labels can yield the same marginal, the problem setup is not identifiable, and the resulting solution is not consistent. So you see variations in domain alignment. In A, you will see that it's a pixel level alignment. Adversarial image translation is applied to translate source images into target images before a common classifier. Source images into target images before you apply this classifier. In B, you will see the feature level alignment, that the source and target features are aligned before applying a common. So source and target are aligned together before applying the classifier. There are different variations, you see. And another variation is this generative alignment of posterior probabilities, that we propose to align the posterior probability of the source and target classifiers using adversarial framework. And then we have source replicator. In the absence of source data, because the companies, they don't give us source data, but they share the source model. So in the absence of this source data, we cannot align the probabilities of source and target directly. Therefore, we aim to replicate source prior probability vectors for target alignment. We perform this additional step of source replication after training a source network. Specifically, we design a conditional generative adversarial framework that takes fake label and noise as input to generate a probability vector of k dimensions. The conditional discriminator is trained to discriminate between generated probabilities and source probabilities from the pre-trained source classifier G. So we train this conditional GAN. It's not ordinary GAN, it's a conditional GAN using the least squared loss function. The conditional framework captures the statistical variations of source because we care about interclass relations. We use the train conditional generator to replicate or generate source probabilities when minimizing the KL divergence between our approximated distribution and the true distribution and the prior source distribution. So we have these domain adaptation approaches that rely on source data to perform source-target alignment. The proposed model can be interpreted as the alignment of posterior probability. This is the posterior probabilities P, S, and PT, where we align the source and target in the final stage of classification. We implement a GAN. So the source prior P sub S of Y is modeled by the source replicator GC. This is source replicator. And we initialize the generator with the parameters of pre-trained source classifier. The similarity between the source and target domains is exploited to provide near optimal initialization. And then we have this discriminator D. With parameters phi is trained to distinguish between the generator outputs and outputs of the source replicator. So you see that the model diagram for gap, that in A we are just doing source training. the feature extractor F and C. This F and C, both C is classifier, F is feature extractor. And in B, we have source replication. That's a source replicator, which is a conditional generator, G of C. It is conditioned on C, so it's G of C. The conditional generator G of C is trying to replicate source predictions. It is designed such that it replicates the source predictions. And in C, we have target adaptation. That during target adaptation, the C component is frozen. So this is frozen to retrain the source classifier.